The Cortex M3 and Cortex M4 processors are widely used in embedded systems. Their memory system is fundamental, defining how the processor accesses code, data, and peripherals. These processors provide a 4 GB linear address space thanks to their 32-bit addressing capability. While most embedded systems use far less memory, this headroom simplifies design and allows future upgrades. They employ a simple yet efficient 总线 protocol called AHB Lite. This protocol enables connections to various memory and peripheral devices. AHB Lite supports 32-bit, 8-bit, and even 8-bit memory devices through appropriate interface controllers, offering flexibility in system design. This 4 GB address space ensures that even if the current system only needs 1 MB, there is plenty of room for expansion without changing the architecture. Here we see the predefined memory map of the Cortex-M processors. The 4 GB address space is divided into several logical regions to simplify system design. The map includes regions for program code, data memory like SRAM, peripherals, and a special area called the private peripheral 总线 for internal control and debug components. The CODE region is intended for program code, but interestingly, code can 总线 also execute from the SRAM region. This gives developers flexibility. Next, focus on programs can 总线 execute from both CODE and SRAM regions. Programs can 总线 execute from both CODE and SRAM regions. Next, focus on, in practice, most devices use only a small portion of each. In a typical microcontroller, only a fraction of each region is physically populated. For instance, there might be 520 KB of 闪存 in the CODE region and 64 KB of SRAM in the SRAM region. One key advantage of the Cortex-M architecture is that the memory map is consistent across all devices, from Cortex-M3 to Cortex-M7. For instance, the private peripheral 总线 region always contains the nested vectored 终端 controller and the processor's configuration registers, regardless of the microcontroller vendor. Thanks to this standardization, software written for one Cortex-M device can 总线 be easily ported to another, and debug tools can 总线 rely on fixed addresses for common debug components. This consistency is a major reason why Cortex-M has become so popular. It reduces development time and increases software reusability across the entire ecosystem. Now let's look at the stack, an essential part of the memory system. This diagram illustrates the stack concept in a typical RAM space. The stack operates in a last-in, first-out manner. Data is pushed onto the stack and later popped off in reverse order. The stack is a last-in first-out LIFO buffer located in. Next, focus on the stack pointer, R13, automatically increments OR. In Cortex-M, the stack pointer R13 always points to the last pushed item. It automatically adjusts with each operation, ensuring efficient memory use. Typical uses include saving the contents of registers before a function modifies them, and restoring those values afterward. This is crucial for maintaining program state. This figure illustrates a multiple 寄存器 stack operation. The PUSH and POP instructions can 总线 handle several registers at once, not just one. Before calling a subroutine, the current values of R4, R1, and R2 are pushed onto the stack using push R4, R2. The stack pointer decreases as data is stored. After the subroutine finishes, POP R4, R2 retrieves these values in reverse order. Notice that each transfer is at least 4 bytes, and the stack pointer remains word-aligned. Here is a simple example that demonstrates multi-寄存器stack operations. The main program calls a subroutine called function1. Because each 寄存器 is 32 bits, each push or pop transfers exactly 1 word. The stack pointer remains word-aligned throughout. PUSH and POP can 总线 transfer multiple registers. Notice that before the subroutine does its work, the instruction PUSH R4, R2 stores registers R4, R1, and R2 onto the stack. After completing its task, POP R4, R2 restores the original values. This guarantees that the main program continues with its original data undisturbed. Next, focus on the lowest 2 bits of the stack pointer are always 0. The lowest 2 bits of the stack pointer are always 0. The example code shows a subroutine that saves and restores. In more advanced usage, you can 总线 combine the return from a subroutine with the stack restoration. This code example illustrates that technique. You can 总线 combine the subroutine return with a POP operation. The subroutine pushes not only R4, R2 but also the link 寄存器 LR onto the stack. The link 寄存器 holds the return address. At the end, a single POP R4, R2 PC instruction restores the registers and loads the saved return address directly into the program counter PC. This returns from the subroutine. Next, focus on the code shows PUSH R4, R2, LR at the start and POP R4, R2. By combining the return, we save a branch instruction and simplify the code. This is a powerful feature of the Cortex M instruction set. The code shows PUSH R4, R2, LR at the start and POP R4, R2. Next, focus on it is a common pattern in ARM assembly for efficient. It is a common pattern in ARM assembly for efficient. Beyond basic stack usage, the Cortex M provides dual stack pointers for robust operating system support. This diagram shows MSP and PSP usage. The main stack pointer is used by default after reset and for all 异常 handlers. The 进程 stack pointer is an alternate that can 总线 be used for application threads. In a system without an OS, only the MSP is used. But when an embedded OS is running, the PSP allows each 线程 to have its own stack, isolated from the kernel. Next, focus on PSP is used for application tasks in 线程 mode when an OS. Note also the technique of combining the return with a POP. By pushing LR and popping to PC, you can 总线 return from a subroutine while restoring registers. PSP is used for application tasks in 线程 mode when an OS. This figure illustrates the dual stack mechanism during 异常 handling. When an OS is present, the PSP and MSP work together seamlessly. In a simple system without an OS, only the MSP is active, and all code uses it. But when an 异常 occurs, the hardware always switches to MSP for handler execution. The processor performs automatic stacking. It pushes key registers onto the stack before entering the ISR. When the ISR returns, those registers are unstacked automatically. Next, focus on at the end of the ISR. At the end of the ISR. Next, focus on with an OS. The hardware switches to MSP on 异常 entry. For an OS-based system, the PSP stores the 线程 as stack. Upon an 异常, the hardware switches to MSP for the handler, and reverts to PSP on return, ensuring clean separation. Although the processor only shows one stack pointer via RSUN, privileged software can 总算 read and write the other stack pointer directly. Here are the CMSIS functions to do that. You can 总线 read the current MSP with 下划线 get 下划线 MSP and set it with 下划线 set 下划线 MSP. Similarly, PSP has its own getter and setter. These are simple APIs defined by ARM. CMSIS provides 下划线 get 下划线 MSP 下划线 set 下划线 MSP 下划线 get 下划线 PSP. Next, focus on in assembly. MRS and MSR instructions are used to read and. In assembly code, instructions like MRSR0, MSP copy the main stack pointer into a 寄存器, and MSR MSP, R0 writes a value back. Most application code never needs to do this. It's mainly for OS kernels. Be cautious. Changing the current stack pointer in the middle of a C function can 总线 disrupt local variables that are stored on the stack, leading to unpredictable behavior. Let's look at the specific assembly instructions for accessing the stack pointers. Remember, direct access is usually reserved for operating system code. The MRS instruction reads a special 寄存器, in this case, MSP or PSP, into a general-purpose 寄存器. For example, MRSR0, MSP copies the MSP into R0. Conversely, MSR writes a value from a general 寄存器 to a special 寄存器. This allows an OS to set up a new stack for a 线程 before switching to it. Most embedded applications never touch these instructions. They rely on the 编译器 to manage the stack transparently. Only when you're writing ARTOS do you need this level of control. Finally, let's discuss the MPU. The MPU is an optional hardware block that enhances system reliability by controlling memory access. Not all Cortex M3 or Cortex M4 chips include an MPU. When present, it allows you to define up to 8 memory regions with specific access permissions. For example, you can 总线 mark a region as read-only for unprivileged code or even prevent execution from certain areas. This is critical in safety-critical applications. However, in the majority of embedded projects, the MPU is not used. If you don't need strict memory protection, you can 总线 simply ignore it and rely on careful software design.